So here we're going to look at some examples involving stoichiometry. And so in the first example, we're going to be looking at a problem where we're given the amount of one reactant and the other reactant is in excess. So here, if you notice, we want to determine if 27.3 grams of B2H6 is reacted with excess H2O, how much, I'm sorry for my typo there, how much H2 is produced. So here we have a limited quantity of B2H6. We're going to react it with excess H2O. How much H2 gas is produced? And we up here we have the balanced chemical equation. So again, what we're going to do, since we have already one reactant in excess, the other one is not, we already know the limiting reactant is B2H6. So we're going to take the mass of B2H6, convert it to moles of B2H6, and then to moles of H2O, and then to mass of H2O. Not H2O, sorry, H2. So again, we're going from mass to moles, moles to moles, moles to mass. And again, the reason we can do this only once is we know that B2H6 is the limiting reactant because H2O is in excess. And so from the chemical equation, we know that 1 mole of B2H6 is equal to 3 moles of H2. That's our mole ratio. So we're going to set up our problem. So in step 1, we're going to convert mass to moles. So 27.6 grams of B2H6, again, dividing it by the molar mass. So again, we have 2 boron atoms and 6 hydrogen atoms, so our molar mass is 26. And we'll see what this is. So this is step 1. So we get 1.06 moles of B2H6. So again, dividing by the molar mass gives us the moles of reactant. Now in step 2, we're going to take the moles of B2H6 and convert it to moles of product. And so if we look at our mole ratio, it's 1 mole of B2H6, 3 moles of H2. Since we're starting with B2H6, it will go on the bottom, H2 will go on top. So here we'll get 3.18 moles of H2. That's step 2. And then step 3, we're going to take the moles of product and convert it to mass. And this will tell us the amount of product in grams that we'll produce. 6.36 grams. And again, this is referred to as the theoretical yield. So if we were to do this reaction perfect, this is the maximum amount of hydrogen gas we could produce. So in our next example, we want to calculate the theoretical yield of manganese when we have 185 grams of calcium reacts with 140 grams of manganese 4 nitride. So unlike our previous example, in this example we have the mass of each reactant. So unfortunately, we don't know the limiting reactant right off the bat. So what we're going to have to do first is we're going to have to determine which reactant is the limiting reactant. And so what we're going to do is, similar to what we did on the last example, we're going to do a calculation for calcium. So we're going to take the mass of calcium, convert it to moles of calcium, convert it to moles of manganese. And the reason we're converting it to moles of manganese is because the question is asking us how much manganese, or what's the theoretical yield of manganese. And then we're going to do the exact same thing for manganese 4 nitride. So we're going to take the mass of manganese 4 nitride, convert it to moles, and then convert it to moles of manganese. So that's what we're going to do first, and then we're going to determine the limiting reactant and calculate theoretical yield. Let's go ahead and start. So we'll go ahead and set up for calcium. It already gives us a balanced chemical equation. We already have the molar masses of our reactants and products. So for calcium, again, we're going to start with its mass. We're going to divide it by the molar mass of calcium. And I'll do each step so we can see all the steps. And we're going to do the exact same thing with manganese 4 nitride. This is the first step, determining the moles of our reactant. Oops, typo there. Right. So we get, for calcium, we get 4.61 moles of calcium. Then we're going to multiply it by the mole ratio. So since we're starting with calcium, it's going to go on the bottom. So we have 3 moles of manganese over 6 moles of calcium. So this would equal 2.31 moles of manganese. And we're going to do the exact same thing for manganese 4 nitride. So we get 0.634 moles of manganese 4 nitride. Then we're going to multiply by the mole ratio. Since we're starting with manganese 4 nitride, we're going to put manganese on top and manganese 4 nitride on the bottom. And this will tell us how many moles of product are formed by this reactant. And we get 1.90 moles of manganese. So at this point, we've calculated the moles of product produced by each reactant. And in this example, manganese 4 nitride is the limiting reactant. So what we're going to do is we're going to take the moles of product produced by the limiting reactant and convert it to grams. So we're going to multiply by the molar mass. And we get 104 grams of manganese. And again, this is referred to as the theoretical yield. So again, since it gave us information about both reactants, we had to determine which reactant produced the fewer moles of product. In this case, it was manganese 4 nitride. And then we took the moles of product produced by that reactant and converted it to mass to get the theoretical yield. So now continuing from our stoichiometry where we just calculated the theoretical yield, here we have a reaction involving phosphorus and iodine. And in this example, for phosphorus, we just assume it's monoatomic. Phosphorus also exists as a tetraatomic molecule as well, but for this example, we kept it as just P. And so we want to know what is the percent yield of the reaction if 44.7 grams of our product, phosphorus triiodide, is obtained from the reaction of 96.3 grams of I2 with excess phosphorus. So again, the key we should pick up on is we have excess phosphorus, so we know that I2 is the limiting reactant because there's more than enough phosphorus to react with all the I2. The second thing we should note in this problem is the 44.7 grams of phosphorus triiodide. This would be referred to as our actual yield. So this is when we did the experiment. This is the amount we actually obtained. So now what we're going to do is our plan of action is we're going to take the mass of I2, convert it to moles of I2, convert it to moles of PI3, and then convert that to mass of phosphorus triiodide, which is our theoretical yield. And again, the reason we want to do this is because percent yield is actual over theoretical times 100. So we got to know the theoretical yield in order to determine the percent yield because we already have the actual yield. And so again, the molar mass of I2 is 2 times 127, which gives us 254 grams per mole. And then the molar mass of Pi3 is 1 times 31 plus 3 times 127. So let me do that. So I'm just getting everything ready that we're going to need to solve this problem. That's 412 grams per mole. So this is one thing we'll need is the molar masses. The other thing we'll need is the mole ratio. So 3 moles of I2 give us 2 moles of Pi3. So in step 1, we're going to take the mass of iodine, which is 96.3 grams, and divide it by the molar mass. This is going to tell us the moles of I2 that we have. So we get 0.379. That's step 1. Now in step 2, we're going to take the moles of I2 and using the mole ratio, we're going to convert that to moles of our product. Now since we're starting with I2 and our mole ratio, I2 goes on the bottom, Pi3 goes on top. So whatever you're starting with in the mole ratio, that goes on the bottom, and the other one goes on top. And we get 0.253 moles of Pi3. So that's step 2, converting from moles of reactant to moles of product. And then in step 3, we're going to calculate the theoretical yield by converting the moles of product to mass. This will tell us the theoretical yield. And we get 104 grams of Pi3. And again, this is the theoretical yield. So now we have the theoretical yield, we have the actual yield, we can calculate the percent yield. And we get 43.0%. So that would be the percent yield of this reaction. So again, since we were just given information about one reactant, we already knew which reactant was the limiting reactant. So then we were able to convert that to the moles of reactant to moles of our product, then find the theoretical yield, and from there calculate the percent yield. So in this example here, we have a reaction involving hydrogen and nitrogen gas to produce ammonia. And so we're starting with 65 grams of hydrogen with 95 grams of nitrogen, produces 65 grams of ammonia. What is the percent yield of the reaction? Now, one thing we got to take in mind here is that it gives us information about both reactants in this example. The good news is that we already have the balanced chemical equation. So again, percent yield is actual over theoretical times 100. Now from the problem, we know that the actual yield is 65 grams of ammonia. Because ammonia is our product, that's the actual yield. So that's one piece of the puzzle that we have. But we do not have the theoretical yield. That's our question mark. And so to find the theoretical yield, we have to use the information about both reactants to determine which one produces the fewer moles of product. So what we're going to do is we're going to do duplicate reaction 1 for H2, where we take the mass of H2, convert it to moles of H2 to moles of NH3. And we're going to do the exact same thing for N2. So with N2, the mass of N2, we're going to convert that to moles of N2 to moles of NH3. And then we're going to see which one produces the fewer moles of product. That's going to determine the limiting reagent. And then the moles of product produced by the limiting reagent, I'll call it LR, we convert to mass. And this will give us our theoretical yield. So just a few things we need. First off, we need the molar mass of H2, which is 1 times 2, equals 2 grams per mole. And we need the molar mass of N2, which is 2 times 14, 28 grams per mole. And lastly, the molar mass of NH3, I just like to have everything set up that I'm going to need. Then we need the mole ratios. So 3 moles of hydrogen gives us 2 moles of NH3. And 1 mole of nitrogen gives us 2 moles of NH3. So now we're ready to start our calculations. So again, we're going to set it up for H2. So we're going to convert the mass to moles. And we're going to do the exact same thing for nitrogen. This is step 1, converting the mass into moles. Let's go ahead and work that out. So we get 32.5 moles of H2. Then we're going to use the mole ratio to convert this to moles of NH3. Again, since we're starting with H2, our moles of H2 will go on the bottom, the moles of NH3 on top. And this will tell us the moles of NH3 produced by H2. And we get 21.7 moles of H2. Now we're going to do the exact same thing for nitrogen. So we get 3.39 moles of N2. I'm going to use the mole ratio to convert it to moles of ammonia, keeping in mind that since we're starting with N2 in our mole ratio, nitrogen will go on the bottom, ammonia will go on top. We get 6.78 moles of NH3. And I made a typo here. Let me correct it. This should be moles of NH3 as well. So now we see that we have 21.7 moles of NH3 produced by H2, 6.78 moles of NH3 produced by N2. So in this example, N2 is our limiting reactant because it produces the fewer moles of product. So now we're going to take the moles of product produced by N2 and convert that to grams. This is going to tell us the theoretical yield. And we get a theoretical yield of 115 grams of ammonia. So now we know our theoretical yield, we have our actual yield, we can calculate the percent yield. We get a percent yield of about 56.5%. So again, in this example, since we're looking for percent yield and it gives us information about both reactants, we have to determine which reactant is the limiting reactant by seeing which reactant produces the fewer moles of product. In this example, it was N2, so we took the moles of product produced by N2 and converted that to grams to get the theoretical yield. Actual yield was given to us in the problem. So you see here we're kind of doing the same steps. It's just at the end to calculate percent yield, we do one more additional step.